Okay, so in the last video I explained to you about the introduction of waves. So I explained about the types of waves, the characteristics of waves, and I stopped by explaining to you about the progressive waves. So as I mentioned, there were two types of waves. There are various classification of waves. So in one classification we classified waves according to the behavior, that is about the mechanical, the electromagnetic, and the earthquake waves, various types of waves. And another classification is based upon the appearance. Now based upon the appearance we actually divided the waves into two types, which are the progressive waves and the stationary or standing waves. So I explained to you in the last video that the main difference between the stationary waves and the standing waves is that stationary waves are reflected back along the initial propagation direction, and progressive waves are never reflected back. Furthermore, in the case of stationary waves, you can apply the equations, the wave equations, the popular wave equation V equals F lambda, or any other derivation of this equation, only to the progressive part. So having explained about the main differences between the progressive waves and the standing or stationary waves, now having actually I actually explained to you about the progressive wave in detail in the last video. So now in this video I'll begin with the introduction of the standing or stationary waves. To explain you about the stationary or the standing waves, I need to introduce you about the principle of superposition. So what is meant by the principle of superposition? So the principle says like this. So I'll mention you about the principle first, and then I'll explain you what the principle says. So the principle says like this. Now actually, if you have two waves, now you know that there is some amplitude of these waves, right? So I explained to you about the concept of amplitude in the last video. So you have an amplitude to any type of wave, right? So I also explained to you about the analogous condition between the longitudinal waves and the transverse waveform, not the transverse wave, the transverse waveform, or the transverse wave, the picture, right? The waveform picture. So any wave has an amplitude, right? So mainly mechanical waves have an amplitude. So these two waves have an amplitude. So now you know that if, say, the amplitude of the first wave is I'll take d1, and the amplitude of the second wave is d2, whether not d1 is greater than d2 or equal, or d1 is less than d2. So the resultant displacement, or dr, at any point is the sum of the separations due to the two, right? So dr is equal to d1 plus d2 or d1 minus d2. So actually that depends upon the value of d and d2. So dr is equal to the resultant of d1 and d2. Now when two waves travel through a medium, their combined effect at any point can be found using the principle of superposition. Now actually the principle of superposition explains you about the resultant, so you can find the combined effect at any point. Now as I explained to you, there may be various occasions in which d1 is greater than d2, or d1 is equal, or d1 is less than d2. Now consider two waves in two occasions. Now first of all, let's consider when d1 is equal to d2, or when the amplitudes are similar. When the amplitudes are similar but opposite in direction, the total displacement is 0. Now you know that the resultant is d1 minus d2. So d1 minus d2, when d1 equal d2, dr is equal to 0. Now you can see in this direction, in this diagram. Now if you have a wave like this, the green wave, say this amplitude, now this is actually, if you extend this line, this is the main base, or the base where the displacement is 0. So this can be considered as d1, and this can be considered as d2. Now this wave moves in this direction, and this wave moves in this direction. When you combine these two, you can see that these overlap, and now when the displacements are also equal, or the amplitudes are equal, this d1 is equal to d2 here. So you can see now these parts are actually horizontal, this part is horizontal. Since the amplitude is equal, this part will also make a horizontal effect, right? So the total wave is like a horizontal line, right? However, when the amplitudes are dissimilar, right? So you consider two waves like this. So consider the same two waves, but the amplitudes d1 is not equal to d2. So we'll consider that d1 actually d2 to be greater than d1, so that when these two combine, these two we take the resultant, you can say that d2 is greater than d1, so d1 minus d2 will make a negative displacement or displacement in the downward direction. So that's it about the principle of superposition. So superposition is actually a concept of overlapping or keeping one over the other, right? So concept of superposition, principle of superposition is important when explaining about standing waves. So as the last occasion of the characteristics or the arrangements of these amplitudes, you can see that now I explained to you in the last two examples about the characteristics when the waves move in different directions. Now when the waves move in the same direction, you can see that, say, the amplitudes are similar. Excuse me. When the amplitudes are similar, you can see that this arc-like part moves in this direction, they get close to each other. Finally they have a greater the increase of amplitude, so the amplitudes of two individual waves are added up, right? However, now this actually results in an unstable equilibrium, because now this is actually the stable condition. If you assume this to be the stable condition, when even when some ball or some object is taken to a high place, it is taken to a mountain or somewhere, you can see that the object is unstable. When you increase the height from the mean base for any wave or any object, that part or the particles or the object become unstable. So this condition is unstable, and this condition or this arrangement will not last for long. So what actually happens is that then this wave or this string tends to become in equilibrium or stable equilibrium, in fact, and they finally stability occurs when the two waves start in opposite directions. So that's it about the actually the variation of amplitudes and the direction of the movement of particles when both the amplitudes are moving in the same direction. So that's it about the principle of superposition. Now consider using the principle of superposition, let me explain you about the concept of stationary or standing waves. Now we have a simple experiment here. So it is actually not an experiment, this is just an apparatus used to I am going to use here to explain you about the concept of stationary or standing waves. So we have some table like thing, right, any surface in which we can do this experiment. We have a vibrator vibrating at constant frequency. We have a pulley and a mass. So pulley and a mass is important. Now we can also put this here, we can connect it to some wall or any other barrier, but we use a pulley and a mass to make this string a constant tension, right? So we need a constant tension to in the string, right, inside the string. So what we do is that we place the string like this. So this is actually the string before the vibrator is turned on, right? Now this is actually one part of the barrier, and this is another part of the barrier. So string will have a constant tension and will go over the pulley like this. When the vibrator is turned on, a wave may be created like this. So this is the black, right? The black part is the original wave. Wave is created like this. It goes like this, like string goes like this after the pulley, but beyond the pulley the wave cannot move, right, because this is a barrier. So now you know that the wave is not completely distracted, right? It's not distracted as well. So what actually happens is that upon reaching this boundary, it is reflected back. So reflecting back is completely, actually what happens is it is flipping over. Now if this moved in the upward direction from the mean base, now consider this the mean base when the vibrator is switched off, or when the circuit is closed, when the circuit is open, right? So what actually happens is that if you have some wave, the original wave to be upwards, the reflected wave will be downwards, as well as when the original wave is downwards, the reflected wave will be upwards. So actually what actually happens is that the original wave is completely flipped vertical. So what happens is that now when this reflected wave comes like this, right, and up to here, beyond this also, this does not make the original wave again, this stays as it is, right? So this is a constant motion. So this will last, say, after about 10 seconds after the reflected wave reaches here, no more versions can be seen, only sometimes when the frequency is so high, is actually the wavelength or the wavelength may decrease or the frequency may increase, resulting in the actually the closer, right, making this node, right, we call these the nodes and the antinodes, which I'll discuss in another video. So these small parts, right, they will make close, but waveform, the characteristics and the appearance may not change. So since the wave is not moving beyond this, we call this as a stationary or a standing wave, right? So when the vibrator is vibrating at a constant frequency, we can obtain a stationary wave like this, right? So this time the wave lies on the medium stationary. So as I explained a little while ago, stationary wave occurs due to the superposition of two waves of equal frequency and amplitude traveling in opposite directions. Now in the concept, as I mentioned in the concept of principle of superposition, we need the amplitudes to be similar, otherwise there will be actually resultant, right? So if we have consider an occasion like this, if you have a resultant here, resultant not equal to 0, you will have some waveform like this, right? So that will not make a standing wave. So to make a standing wave, you should have something like this, right? The amplitude should be similar and these two strings should be moving direction. But in the case of a stationary wave, what actually happens is that this is the original wave, it is reflected back, so the reflected wave looks like this. So according to the principle of superposition, the final displacement or the final outcome is a zero displacement like this, right? So that corresponds to the string when the vibrator is turned off, right? So this diagram shows about the behavior of the stationary waves. Now you can see that this stationary wave goes like this. It after some time, t equals t by 2. So t is actually the period, right? After t by 8, you can see that the displacement is getting lower, and after quarter of the period, at the quarter of a period, the mean displacement is 0. Then this part of the wave is flipped over, and after half of the period, you can see that this part of the wave is flipped over, right, flipped vertical. So that's it about the stationary waves. So that's it about the characteristics of stationary waves. So let me introduce about the properties of stationary or standing waves. Now consider the stationary wave as I explained a little while ago. You have an original wave like this, and at some barrier here, you will get the reflected wave. So the original wave and the reflected wave together makes the stationary or the standing wave. So as in the case of transverse waves, several points of the wave can be seen here. One of the greatest characteristics that can be seen here is the repetition of the pattern, right? Now this point is completely analogous to this point, although they are not in phase. This point is analogous to this point because although they are not in phase, they actually touch the mean displacement or the base, right? And this part is analogous to this one, here and here, all those are analogous. And similarly, this part in which we have the amplitude, and the part that corresponds to the amplitude is analogous in this part or this part, right? So we don't actually consider the original and the separated wave, original and the reflected wave, in fact, separately when talking about the standing wave. So what actually happens is that when we explain about the concept of stationary or standing waves, we take the original and the reflected wave to be as a composite, and finally form the stationary or the standing wave. So these parts are actually these two waves are now actually like a single wave, right? A standing wave, right? So these two parts, this part, and this part, similarly this part, and this part, and this part correspond to the points in which we have the amplitude. So we call those points, these points and these points, in which the displacement is completely zero and the displacement at its highest, with special names. When the displacement is perpendicular to 0, we call those parts nodes, right? So these parts are nodes. This one, this one, this one, this one, and this one are called nodes. Similarly, when the displacement is at its highest, at the amplitude, we call those parts antinodes, right? So these two parts, these two parts, these two parts, and these two parts are antinodes. Furthermore, you can see that the distance between successive nodes actually vibrations in phase, and these two parts, right? These two parts is actually equal to lambda by 2, right? So the distance between an antinode here and a node, or a node and an antinode, but they should be in successive. Between the successive node and the antinode is actually one half, or actually one quarter of the wavelength. Now the distance between any two successive nodes or any two successive antinodes is half the wavelength, which is lambda by 2, and the distance between any two successive node and the successive antinode is one quarter of the wavelength, or lambda by 4, right? So an important point here is that the second and the third points are in sharp contrast to the behavior of a progressive wave, where the phase of points near each other are all different and every point vibrates with the same amplitude. Now in the case of the stationary wave, you can see that all the points doesn't move, right? It doesn't vibrate with the same amplitude, because although the original wave can move up to this point, when it is reflected back, right, these parts are actually like stationary, as it is in the case of a solid, right? It's compacted here and it's stationary, so all the parts doesn't move with the same amplitude. So this part will not move. When the reflected wave reaches this point, this part will not further move in this direction, so this part cannot achieve this amplitude as achieved by this particle. So that's what mean by the particles phase of points near each other, and they vibrate with the different amplitudes, right? So this part cannot reach this part because the wave is not moving in this direction. When the reflected wave arrives here, this part doesn't move in this direction, or neither in this direction, right? Neither in this direction nor in this direction. So this part or any other part will be as it is. Now in the case of a progressive wave, the wave moves like this. So although this part is here, after some time this part may come to here, but in the case of a standing wave, this part is as it is, so this part can never achieve a point like this. So they are not with the same amplitude. So that's it about the waves, longitudinal waves. So in the concept of waves, actually the classification of waves, we can also further divide the stationary waves into two types, stationary longitudinal waves and stationary transverse waves. So stationary longitudinal waves can be studied using a closed pipe. So closed pipe is an apparatus like this. We have an apparatus like this, and we have a closed end here. So you can see that closed ends, the displacement of these particles cannot be as high as it is, right? So they tend to converge here, and at the open end they tend to divide. So that now it is in model in the concept of pipes, right? Open pipes and closed pipes. But for now, they understand that at any like this, in the case of these particles, at any point where there is a barrier, you get nodes, and at any point where it is free, you get antinodes, right? So this point is free to vibrate, but this point is prohibited to vibrate, right? It's forbidden. So this part we get a node and we get an antinode. So that's about the stationary longitudinal waves. So I'll explain you more in detail, right, about the stationary transverse waves and the stationary longitudinal waves in the case of pipes. So that will be discussed in another video. So stationary transverse wave is also similar to the transverse wave that I explained in the last video. So you can say that at these 2 points you form a node, right, and at this point you have an antinode. So similarly, I'll explain you about the stationary transverse waves in the concept of strings. So explain you about the stationary longitudinal waves in pipes and stationary transverse waves in strings. So those will be discussed in the next series of videos on waves. So this is just an introduction to the stationary longitudinal and the stationary transverse waves, and let me conclude this video with the introduction of pressure in stationary waves. Now if you have a stationary wave like this, you can see that at these points, at nodes, the pressure is too much high, right? So all the particles, as in the case of rarefactions and compressions in the longitudinal waves, at nodes the particles are compacted together, so there's a high pressure. So you will experience a pressure like this, the highest pressure at a node, and at an antinode the particles are actually relaxed, right? So it will correspond to a decrease of pressure. Actually the pressure is normal, right? So at the antitude at the antinode you will get the least pressure, or you can say that the normal pressure is 0, right? So the wave moves like this way, the stationary, so the pressure variation is like this way, right? So this is the normal pressure. At a node you get the highest pressure, at the antinode you get the lowest or 0 pressure. So that was the station. So I'll explain you the stationary longitudinal waves and stationary transverse waves in another video, in the series of videos on waves. So thanks for watching this video, and